Hi and welcome to this talk. My name is Soel and I'm going to give you a glimpse into our recent work where we stand or fall an analysis of CSRF defenses in web frameworks. I worked on this paper with my co-authors Jalal from Saarland University and Giancarlo from CISPA Helmholtz Center for Information Security from Germany. Let's start by refreshing our knowledge about a very old but critical security flaw, cross-site request forgery, or shortly CSRF. During a CSRF attack, a victim is lured into visiting a malicious web page crafted by the attacker. The malicious web page includes resources belonging to the target honest but vulnerable website. This inclusion forces the victim's browser to send cross-site requests toward the target site, automatically including the session cookies of the victim in this request, because the browser complies with the same origin policy for cookies, which in turn leads to a sensitive state-changing operation to be executed but without the victim's intention or awareness. Now, over the past many years, there have been a plethora of robust defenses proposed to mitigate CSRF attacks, such as custom HTTP headers, hard-to-guess tokens, and SameSide cookies. But in practice, we observe a steep increasing number of CSRF vulnerabilities being reported every year. In this paper, we try to identify additional explanations to the increasing occurrences of such an old vulnerability. That is, are CSRF defenses implemented correctly in practice? Despite the popularity of CSRF attacks, little has been done to understand how CSRF defenses are implemented in practice. In this paper, we intend to study the state of these CSRF implementations. More concretely, we aim to answer the following three questions. First, what CSRF defenses exist and which ones are used in practice? Then, what are the threats to these defenses and how prevalent are these threats in the wild? And finally, what are the developers' challenges when using these defenses in practice? To give you an overview of our approach, we first identified existing CSRF defenses by systematically surveying the existing literature. Then we studied the usage of these defenses in the 44 most popular web frameworks across 5 programming languages. The methodology for the selection of these frameworks is as follows. We first select the top 5 web programming languages based on the 2019 GitHub October's report, which is JavaScript, Python, Java, PHP, and C#. Then we rank the web frameworks we identified for these programming languages based on a series of criteria. That is the number of GitHub used by, GitHub stars and forks, the number of their downloads in their respective package managers, such as pip for Python and packages for PHP, as well as the number of their relevant questions in Stack Overflow. Finally, we select the top 10 frameworks for each language. This results in 44 frameworks because for C# and JavaScript, we only identified 5 and 9 web frameworks respectively. Then we identified the threats to CSRF defenses by comprehensively reviewing academic literature, OWASP security best practices, the National Vulnerability Database, and GitHub issues. Now, to analyze the framework's source code against these threats, we first manually identified the CSRF-related source code files following control flow insensitive navigation and noted possible entry points for the execution, as well as the CSRF-related security-sensitive functions. For instance, functions containing cryptographic operations and functions that generate and validate CSRF tokens. Then we evaluated the workflow of CSRF defenses following a manual forward control and data flow sensitive inspection. Finally, we verified our manual code review by dynamically monitoring the execution at runtime. Lastly, to understand web developers' challenges when using CSRF defenses, we reviewed the documentation and API specification of frameworks based on 6 measurable quality criteria. Also, we report on some of the interesting aspects we learned while disclosing the vulnerabilities to the affected parties. Okay, let's start by our first research question, existing CSRF defenses and their usage in practice. We comprehensively surveyed existing literature and identified 16 distinct defenses. By dissecting CSRF attacks, we categorized these 16 defenses into 4 classes. That is, defenses that check the origin of the incoming state-changing request, defenses that add hard-to-guess parameters to the requests, defenses that automatically strip session cookies from the requests, and finally defenses that verify if the request is intended by the user or not, for example through reauthentication or captchas. Now, for timing reasons, I won't be able to go through each individual defense. Please refer to the paper for more information. Looking at the demographics of CSRF defenses in the 44 frameworks we studied, we observed that 28 frameworks come with a built-in defense. However, in 17 of them, the defense is disabled by default. In contrast, we have 16 frameworks which offer no built-in defense. Still, we identified existing defenses for the 13 of these 16 frameworks via external official and unofficial libraries. Interestingly, we observed that the most popular defense is double submit cookie followed by plain token, whereas the least popular defense is cookieless user sessions, which is an emerging pattern where the web storage and custom client-side JavaScript code replaces cookies and cookie management policies respectively. Now, web frameworks may implement multiple CSRF defenses at the same time as a defense in depth, and we observed that almost half of them, that is 19 frameworks, enforce 2 or more defenses in sequence at the same time. Interestingly, double submit cookie and HMAC token are used together more than any other pair of defenses, that is in 12 frameworks, which is then followed by double submit and SameSide cookies pair, which is used in 6 frameworks. Now, SameSide cookies are relatively new mechanisms that could help protect web applications from CSRF attacks. However, our evaluation shows that only 10 frameworks offer SameSide protection, in 6 of which it is used as a defense in depth. Coming to the second research question, we studied the exposure of frameworks in the 18 threats we identified from the existing literature by manual code review and dynamic testing. As a result of this process, we identified a total of 157 security risks affecting 37 frameworks across 4 categories of threats: token generation, token leakage, cookie integrity, and implementation mistakes. Out of the 157 security risks, 17 are directly exploitable. The rest of the vulnerabilities, that is 140 security risks, are only exploitable under the default configuration of the web framework. We observed that the most common security risks are implementation mistakes, whereas the least common risks are those corrupting the integrity of cookies. And what we haven't seen at all is the usage of weak token generators, which is good. Overall, we observed that 89% of the frameworks with the CSRF defense are vulnerable to at least one threat. Now, again, for timing reasons, in the remaining of this presentation, I only focus on the 2 most common categories of threats, that is token leakage and implementation mistakes. Please refer to the paper for more information about the 2 other categories of threats, that is cookie integrity and token generation. Okay, let's first see how token leakage can happen. Assume that we have a malicious attacker-controlled web page and an honest banking website. The malicious page first sends a GET request to retrieve the web page that contains a valid CSRF token. Note that the attacker cannot simply read the token in the HTTP response across origins because it is protected by the same origin policy. Therefore, for any subsequent state-changing request, for example for a bank transfer, the attacker cannot guess the token correctly and includes a false token, say F, in the request, and therefore the banking server can correctly reject the request with a 404 HTTP status code. However, if now the banking site has an over-permissive coarse misconfiguration, the response that contains the CSRF token is now relaxed by the coarse policy, and therefore the attacker can leak the true token T and use it in the state-changing request, which in turn results in a successful CSRF attack. Now, coarse misconfigurations are one way that tokens can be leaked, but there are others, such as cross-domain referrer leakage or side-channel attacks affecting the CSRF token comparison. And in our analysis, we identified instances of each of the 3 above-mentioned threats. In summary, during analysis, we identified a total of 37 token leakage vulnerabilities affecting 34 frameworks. So let me show you a real-world example of the token leakage vulnerability in the Play framework. The vulnerability affects the course module of Play when it is enabled. In particular, it sets the account header, that is access control allow origin HTTP response header, to dynamically reflect the origin of the incoming HTTP request. Also, it sets the ACK header, that is access control allow credentials HTTP response header, to be set to true by default. With this configuration, any web page can read the HTTP response by JavaScript across site origins. Therefore, to exploit this, an attacker can simply send a GET request to retrieve the web page with a valid CSRF token, use JavaScript to read the token in the web page, and subsequently use the token in the actual state changing request, which will in turn result in a successful CSRF attack. A more common types of threats to CSRF defenses are implementation mistakes. For instance, assuming the same example of a malicious web page and a banking website where the goal of the attacker is to mount a successful CSRF attack for a bank transfer, the attack page first now sends a post request with a false CSRF token, say F. The server will check the request method and will do the CSRF verification, and because the token F is an invalid CSRF token, the server will correctly reject the request with a 404 HTTP status fault. However, the attacker can now change the request method to GET because there is a missing CSRF check on GET-based HTTP requests. And this bypasses the CSRF verification and results in a successful CSRF attack. Interestingly, in another recent work appearing in SMP 2022, we showed that GET-based state-changing requests are still prevalently used in practice. Again, missing CSRF checks on requests with safe HTTP methods is just one example of implementation mistakes, but there are others, such as logical mistakes or reusable tokens, which can lead to replay attacks, and authenticating WebSocket connections purely based on cookies. All in all, during our analysis, we observed a total of 80 implementation mistakes affecting 37 web frameworks. Okay, so let me show you a real-world example of an implementation mistake in the CakePHP web framework. In particular, this vulnerability affects the CSRF verification process in that it is only performed on requests with unsafe HTTP verb, such as put, post, delete, and patch. To bypass the CSRF verification, the attacker could have changed the request method to any string via the HTTP method override feature. This worked because there was a second vulnerability in the routing module of CakePHP that performed no check on the provided input string to be a valid HTTP request method. Now, this is only one example of missing checks on request HTTP methods, but actually during our study, we identified that 25 out of the 39 frameworks with a token-based defense are vulnerable to this threat. Another example of implementation mistakes affecting the CSRF verification process is the logical security flaw in the Vert.xweb web framework. In particular, whenever a token is generated in this framework, it is stored in three places: in the HTML form, in a CSRF cookie, and in the server-side user session object. Then, whenever a state-changing request arrives, the server compares the token in the CSRF cookie against the token in the session object. However, this is vulnerable because the token in the HTML form is completely ignored, and the victim cookies, be it the CSRF cookie or session cookies, as we know, are always sent during a CSRF attack. Okay. Let's now move on to our third research question: web developers' challenges when using the anti-CSRF defenses. Even when frameworks implement robust CSRF defenses, their incorrect use can severely impact web application security. Incorrect use may stem from missing or misleading documentation about the name or description of the CSRF defense itself and its cryptographic guarantees, under-documented API specifications, wrong or missing code examples, insecure defaults and configuration parameters, and finally, other general security considerations. For instance, known behaviors that can weaken the security guarantees when not protecting state-changing operations against CSRF attacks. We systematically reviewed the documentation of the web frameworks and ranked them based on these 6 quality criteria. Interestingly, we found that 4.5% of the frameworks included information for all of these 6 criteria, which is great. At the other side of the spectrum, however, we observed that around 30% of the frameworks fulfill only one of these 6 criteria. Finally, around 62% of the frameworks do not fulfill half of the documentation quality criteria. And what we learned is that the state of the documentation of web frameworks about anti-CSRF defenses is far from adequate. In fact, such a result is alarming as it indicates that even if the frameworks implement robust CSRF defenses, misconceptions can arise as developers try to use these defenses in practice. Incorrect use of defenses can also arise from variety in the semantics and operations of APIs. In fact, although our evaluation identified different CSRF defenses, we observed that the vast majority of frameworks, that is 39 out of the 41 frameworks with a defense, implemented defense from the request unguessability category, that is a token-based defense. And our API specification analysis revealed that CSRF-related API semantics and operations diverge in integration, defense configuration, generation, and validation of CSRF tokens. For instance, our review of the APIs showed that frameworks provide 3 distinct ways to add tokens to the request. For example, by calling the token generation function and arbitrarily placing the token in the HTTP request, by using helper functions and pseudo variables that are interpreted by a template engine when generating the HTML code for the browser, or by using the framework provided special form objects. Similarly, the token validation is done in distinct ways. For instance, by calling the CSRF verification function, by using method decorators, or it can be completely automatic. Overall, we observed that there is no established consensus in the way unguessable request defenses are exposed to developers. So we responsibly disclosed all the 157 security risks we identified in this paper to the affected frameworks. And while disclosing, we learned interesting aspects about CSRF defenses. In particular, we observed that the same threat was patched in some frameworks but not in others. For example, replay attacks were patched by Ver.x Web and a Slim framework but not by Django and Spring frameworks due to risk acceptance. So we observed that there is an inconsistent threat model as there is a disagreement among framework developers on what is a threat to CSRF defenses. Another example was the bridge vulnerabilities, which was patched by KPHP and Ver.x Web framework, but not by Apache Structs, as they decided that it is not the framework responsibility to fix that. Therefore, we observed the second type of disagreement on who should patch the threats, the web app developer or the framework developer. All in all, what we learned from our vulnerability disclosure process was that there is an inconsistent threat model and divergent expectations on who is responsible to fix the security issues. In summary, in this paper, we undertake one of the first security evaluations of CSRF defense as implemented by web frameworks, with the overarching goal to identify additional explanations to the occurrences of such an old vulnerability. We start by systematically and comprehensively reviewing the existing literature and identify 16 distinct CSRF defenses and 19 threats against them. Then we evaluated the source code of the 44 most popular web frameworks of the top 5 web programming languages and identified a total of 157 threats across 4 threat categories, that is, token generation, token leakage, cookie integrity, and implementation mistakes. Out of the 157 security risks, 17 are directly exploitable and the rest are exploitable only under the default configuration of the web framework. Overall, we learned that while token generation is in general the most robust building block, the remaining building blocks are equally exposed to a variety of risks. And we observed that 89% of the frameworks for the CSRF defense are vulnerable to at least one threat. Then, to understand web developers' challenges when using CSRF defenses, We reviewed the documentation of the web frameworks and observed that the state of the documentation is far from adequate, with almost 62% of the frameworks, more or less, not fulfilling half of the documentation quality criteria. Furthermore, our analysis of the specification of the CSRF APIs revealed the variety of semantics and operations that diverge in defense configuration, token generation, and validation. Overall, we observed that there is no established consensus in the way unguessable request defenses are exposed to developers. Finally, during our vulnerability notification process, we learned that there is an inconsistent threat model and divergent expectations on who is responsible to fix the issues about CSRF defense implementations, that is, framework developers or web application developers. And with this, I would like to conclude my talk. Thanks a lot for your attention, and if you have any questions, please don't hesitate to ask.